So I want to build on the exploration that we did with area under the curve and actually use this to introduce the concept of the integral. Okay, we're going to introduce the concept of the integral. There's a lot of notation here at the beginning that you need to make sure that you get down right now. All right, because if you don't, then you're going to be kind of lost as we go along. But I want to start here with a definition of a definite integral. What are we talking about here with the definite integral? All right, well, it says here the value a is known as the definite integral of a function f of x from a to b, written a equals, and you have this elongated s. It actually is an elongated s. We've talked about Leibniz and Newton, the co-inventors of calculus. Newton actually came up with a lot of the notation that we use. And since the Greek letter sigma was already used for sums, he used the English letter s and just stretched it out, because an integral actually is a sum. All right, and as we saw in the exploration, we're able to find the area under a curve by taking those rectangles, or whatever we happen to use, and adding them up. So it's the sum of the areas of rectangles. Okay, and in fact, we're going to see this a little bit here and expand even more than what you see already on your notes. There's actually things called Riemann sums that we'll look at real briefly. It's not something that you're going to have to be able to do, but I want you to see it so that you can kind of appreciate what's going on behind the scenes as you do integration, okay? Really, for IB calculus, the level of integration you guys have to do is very basic compared to, say, like AP calculus, all right? Now, that doesn't mean it's easy and you can just cruise through this, all right? You still are going to have to work at it here, but it's nowhere near as difficult as it could be. We'll just say that. But what we have here, the notation, is showing us the area, that pink area there, the integral from a to b of f of x dx. Now that dx is what's called the differential, all right? We will see how that's used later on when we get into u substitution, but that is a significant part there because that tells us what variable we're taking the integral with respect to. Just like when you took derivatives, it was dy dx. You were taking the derivative with respect to x. Here, we're taking the integral with respect to x in this case. All right? So let's look at a quick example of the function x squared plus 1. And we're going to approximate the area underneath the curve from 1 to 4. So what we're doing here is we are approximating an integral, and it's an integral from 1 to 4 of x squared plus 1 dx. Okay? That's what we're going to do, and to do that, we're going to use rectangles. And here we have upper rectangles. These are called upper rectangles because they extend above the function, and in this case, since the function is increasing, they're right-hand rectangles. Okay, but you can see here the height of this rectangle here is 5, the height of the middle rectangle is 10, and the height of the last rectangle is 17. And each of these is 1 unit wide. Okay, so if I'm doing areas of rectangles, then my area is 1 times 5 plus 1 times 10 plus 1 times 17, which, of course, is 32. Okay? As you can see, though, we've got a little bit of extra stuff that we really didn't want. So I know the actual integral from 1 to 4 is going to be smaller than 32. Okay?
What did you say? Sorry, I heard it, I just didn't get it.
It's okay. The actual integral here is going to be smaller than 32 because we've got these extra bits that we included because we're using upper rectangles.
Okay.
Okay?
Thank you.
Now, because this is increasing, if we do the left-hand rectangles, that's going to give us what are called lower rectangles. Okay? And you'll notice here, if I'm using the left-hand side, the height of the first rectangle is now 2, the second rectangle is 5, and the third rectangle is 10. Okay? So if I'm finding the area, again, the width is 1 for each of those.
See you, boss.
See it? So it's 1 times 2 plus 1 times 5 plus 1 times 10, which is 17. 17. There we go. 17. Now, again, since we're using lower rectangles, we're missing something. Okay? So it's like Goldilocks. One's too much, one's too little. How do we get it just right? Any thoughts? Okay, if we average these two numbers, that's probably going to get us a pretty good approximation. Okay? So a better approximation would be the average of 32 and 17, which ends up being 49 divided by 2, which is 24.5. Okay? Now I can tell you this integral would be 21 1/3 minus 21 1/3 minus 1/3 would be 21 plus 3, 24 exactly. Okay? So even by averaging these two, we are slightly off still. Okay? But you could tell, you know, we're only a half a unit off. That's a pretty good approximation. Okay? Chloe, were you going to ask a question? Or? Oh, I thought you...
How do we know what the right one?
Huh?
How do we know what the exact area is? Like, well, like, what are you comparing it to?
Well, I know the rules in my head, so I did it.
Alright.
So I know what the answer should be exactly. We're going to talk about this and see how we could get an even better approximation. And actually, that'll show us where this whole integral thing came from. Okay? Yeah.
Since we know, like, the left rectangle area and the right rectangle area, and we know it's supposed to be somewhere in between, I know it'd be a little broad, but could you write it in terms of, like, a variable and make it into an inequality? Like, the 17 is the lower one and 32 is the higher one. But we know it has to be in between somewhere.
Yeah, you could come up with some kind of a formula like that. Sure. And give yourself an inequality so you know it's within a range. Okay? What are some other things that we could do to get a better approximation?
Calculator.
Okay, the calculator actually does this. The calculator doesn't know all the integration rules. The calculator does what we're describing here. Okay? What do you think?
I mean, I guess you can make a triangle and take the area of the triangle.
Okay, since this one is kind of curving upward, if we did a triangle like this, or maybe even like rather than going beyond 1, make it a trapezoid. Okay? Or I guess if you did make it a triangle and went here.
The thing is, that would work for that one, not the other one. The other one would have way too much outside of the triangle.
Okay. Yeah, like if we tried that up here, we'd lose a lot. So that's a great point. But that's a good thought. What are some other thoughts that you guys could come up with? How could we minimize the extra that we're getting or the parts that we're missing out on? Chloe?
The extra that you're getting
same, or there's different values?
Not exactly. It's pretty close, though. It is pretty close. Alex?
Can you take the areas of the rectangles and then, oh, never mind. Because I was thinking if you take the areas of the rectangles, add those together, and then, get the triangles on top of the rectangles. I don't know if that would work.
Okay, so you're saying like treat this like a triangle and subtract these triangles?
Yeah.
That could work. You could actually see how that would work. And actually there's the way you're thinking about it is good, but there's a different way of accomplishing the same thing, and that is by, instead of treating them as rectangles in the first place, treating them as trapezoids.
Oh.
There's actually a method we just learned in AP Calc, the trapezoid method, okay, where we divide this up into trapezoids instead of rectangles, okay? So yeah, that's a great idea, and it accomplishes the same thing that you were just describing. What were you going to say?
I would say smaller rectangles just gets it closer. But
Yes, okay. Smaller rectangles. What if we did it, instead of 3 rectangles, what if we did 6? That were each half a unit wide. Look at what we'd get if we did the rectangles there. Okay? If we did rectangles, making them each only half as wide, are we still getting a little bit extra?
Yeah.
Yeah, but we're getting less extra than we were the first time.
So then do we have to cut those in half as well and make them even smaller?
Oh, so if we cut these in half,
Oh my god.
we're getting even less extra. So what, you guys are right there to figuring this whole thing out for yourselves. So what,
Just make a lot of rectangles then.
make a lot of rectangles. Well, what did we learn in calculus that helps us find, a lot of them, or as many as possible?
Oh God. I don't know.
I'll get to your question real quick. Limits. Is that what you were gonna ask? Or? Okay.
I was gonna add another stab in the dark at what we could do together. Good estimate.
What's your thought?
I was thinking if you were to take multiple derivatives of the curve and make like triangles using them, like tangent lines,
Okay.
and then maybe that could be accurate because
No, that's a good idea. If you'd used derivatives, and then that would get you a better angle on your triangles and stuff. That could work. This right here, though, notice the width of each of these rectangles would be, let's say we had n rectangles. Okay? Then the width of each rectangle would equal, in this case, 4 minus 1 divided by whatever n was. Right? And since we're using right-hand rectangles, the heights would equal f of 1 plus that 3 over n. Okay? That would be the height for the first rectangle. And then the second rectangle, I'd have to add another 3 over n, and then another 3 over n, and then another 3 over n.
Like a sequence in series.
So, yeah, we're going to make a series here. Check this out. Okay? I'm going to make I, and I'm actually going to take the sum from I equals 1 to n, because I want n rectangles. And what I'm going to do is I'm going to multiply the width times the height.
Oh my.
Okay?
Is that for all of the
And
is that just for the rectangles as
That's
a whole?
that's for all the rectangles. I'm adding up the rectangles, and guess what? If I take the limit as n approaches infinity,
That gives you the area.
that's going to give me the area. And the higher n is, the closer my approximation is to the exact. And when I take the limit, it does give me the exact. So when you guys see this notation right up here, that's what it's doing. And that's why they use the elongated S, because they're doing a sum. All right? And they had already used sigma for summation notation. So Leibniz decided to use the S and stretch it out. Yeah?
How would the height formula change if you were using the left-handed triangle instead?
Oh, that's a great question. If we were using the left, you'd do I minus 1. It'd be 3 over n times I minus 1.
And in this case, I is just a variable for the height. It's not representing I like.
No, yeah, it's not like the imaginary number. It's the counter or the index in our summation. It's telling us which rectangle we're working with. Okay. Now to generalize this, this is actually using what we call a Riemann sum. Riemann was another mathematician. Okay. He came up with this process for taking the sum from I equals 1 to n of, instead of using the exact numbers, our boundaries were a and b. So you do b minus a over n times f of the left-hand side, so a plus b minus a over n times the I. And that's the Riemann sum. And if we take the limit as n approaches infinity, then that will approximate the integral from a to b of f of x dx. Okay?
Can you repeat what you just said? Please.
The sum is that sum part in there. If we take the limit as n approaches infinity, that will give us the integral from a to b of f of x dx.
Okay, that makes sense.
Yes?
Does the limit always have to be n approaches infinity? Or if we have a set range, how would it be only till like the greatest value we would want?
Well, here's the thing. You could, if you wanted a really good approximation, you could set n equal to like 1,000 or something, and that would give you a really, really good approximation. We take the limit as n approaches infinity because that'll give us an exact value.
What is the I stand for again?
It's just the counter, or the index in the sum. So remember, when you do sigma notation, you let I equal 1, and you calculate that thing in there. Then you let I equal 2, and you calculate the thing, and you go all the way up to whatever n is. Yeah.
What about the fact that the function is also infinite towards negative infinity?
That's okay, because this is going from a particular value a to a particular value b. Okay? Alright, so here's the nice thing for you guys. You are never going to have to actually use that formula down there. Okay, unless you do AP Calculus next year. Alright? Or I think even Calc Honors, she has you do a little bit of this. But I want you to understand what you're doing, because the better you have an understanding of what integration is from a geometric standpoint, the easier life will be for you as you're trying to solve problems. Okay? So we see here, that was the geometric side. The algebraic side of all of this is that these are kind of inverses. And I say kind of inverses because, as we'll see, if we have the derivative and we take the antiderivative or integral, it will take us back to a function. But it may not take us back exactly to the function we want. it'll take us back to the right family of functions. And as we'll see, what we end up with here is we end up with a situation where if we know one point on the original function, then we can find the exact one. So there's a little more information we need. That's why I said it's kind of an inverse. All right? Now, the antiderivative, we use a capital F for. All right? And I'll do one example, and that's about all we'll have time here for. Okay? So let's think about this. What function, if this is a, is x cubed, what function has a derivative equal to x cubed?
X to the fourth.
Okay, so if I'm going to say the antiderivative of a is x to the fourth. Now let's try this. The derivative of x to the fourth is 4x cubed.
No.
So what do I need? Yeah, I need it over 4 or times 1/4, either way. For room, I'll put times 1/4. Okay? So, the antiderivative of x cubed is 1/4 x to the fourth. If I take the derivative of this, I'll get this, right?
Yeah.
Are there any other functions I could take the derivative of and get this?
Yeah, like +1, +2, plus any number.
Yeah, plus, and this is the key thing I wanted to get to here. This is the family. It's going to be 1/4 x to the fourth plus any constant. So we're going to put a plus c at the end of all of these. Okay? All right. Try the practice. It works you through thinking through some of these. We're going to try to use that to develop some rules we'll look at tomorrow. All right? Have a good day, guys.
Bye.
All right. There are the other ones worked out as well.